Hi, everyone. Welcome. I'm Rochan Sankar, founder and CEO of Enfabrica. Really excited to be here at the AI Hardware Summit. Enfabrica is a 3-year-old startup. We build foundational fabrics for AI. And so I'm here to talk to you about foundational fabrics for AI and introduce you to the concept of and the product of an accelerated compute fabric switch. Let's start by talking about the basics of AI systems as they stand today. So if you look at the anatomy of an AI compute node, pretty much across the board, across any of the hyperscalers, including what Meta kind of showed this morning, or what other hyperscalers have looked at, if they're GPU-based AI compute nodes, they basically look like this. There are 4 components that we should talk about. I'll turn your attention to the bottom left. The CPU is effectively the quarterback of the node. This is where the system operating system, the memory manager, where the root complex for PCIe and managing all the devices really resides. And so even though we talk about GPUs all the time, it's important to note that actually the CPU is still, whether it's integrated or whether it's separated, is actually the master, sort of coordinator of many different communications and processes here. Its memory can be used for a lot of functions, especially when we talk about things like LLM inference. It's used for prefill, it's used for optimizer sharding, it's used for some of the colder model parameters like embedding tables, and then is actually moved into GPU HBM for the computation piece. Then look at the right-hand side, the lower right-hand side. The GPU, which everybody I'm sure is patently familiar with, is basically the centerpiece because it's the primary consumer and producer of data in the system. The collective operations, collectives are the way that the GPU communicates, is actually an op that is typically initiated by the CPU. And it actually points to buffers in the GPU where data resides to be able to move it. So this is an important set of communication that happens in order to set up collective operations. That GPU contains obviously a lot of compute, a lot of parallel compute kernels that are mapped to it, but the memory, HBM memory that is on especially the high-end GPUs that are used in AI, stores model parameters, it stores the KV cache and other types of state for inference, as well as embedding tables if it's a DLRM application. So that HBM is extremely valuable real estate, and it's where all the data is effectively for all this kind of high-performance crunching of AI workloads happens. The NIC and the PCIe switch are the important communication devices from a standpoint of the scale-out direction. So there's a network fabric at the top. The NIC or the DPU is effectively an RDMA transmit and receive device to the network. This NIC actually places data directly in the GPU's HBM through a mechanism that's called GPU direct. It actually also posts the buffers where data, when it's received from the network, needs to land. The PCIe switch is what bridges all these devices together. It's sitting in the middle, so that device in the middle is basically interconnecting all of the processors and NICs. That communication has some very strict ordering rules to it between the CPU, which is acting as the root, and the GPU and the NIC. The net of this slide is to kind of show that there's actually a very highly choreographed communication that happens between devices at the hardware level in order to make a system actually operate in terms of moving data. So now let's take the example of an AI node when we have multiple GPUs. As many of you know, AI systems use lots of GPUs. And when you, in this example, look at 4 GPUs, for example, they are actually typically tied to a single CPU. So a single CPU is serving that, so that's why the ratio of a CPU to GPU can be 1:1 to 1:4. But the ratio of GPUs to NIC is actually 1:1. So we call this a stovepipe design because it's basically one GPU sort of statically mapped to a single NIC. And this is how the communication to the network fabric currently happens in systems today. With this types of problem, you could potentially theorize that if lots of network fabric traffic are hitting that one RDMA NIC because that GPU is actually being targeted for, in a communication by multiple other sending GPUs, then you could have a problem that's called incast, which is effectively a congestion problem. So current designs are susceptible to incast. The PCIe switch, which is sitting in the middle, you can see that it's basically spider webbing between all these devices, is actually an input queued device and a blocking fabric, which fundamentally means that it's actually not a fully work-conserving switch, and communication patterns over that can also suffer from performance degradation. The last point I'm going to point to on the slide, the high bandwidth GPU fabric in purple at the bottom. This GPU native fabric, many people know the NVIDIA version of this called NVLink. What's the purpose of that? The purpose of that is to make multiple GPUs look and act like one GPU. And that's extremely important because effectively there are very tight latency controls that have to exist between those GPUs in order to not stall GPU threads. So if we're looking for extreme parallel performance out of the GPU, that GPU native fabric is essential for coordinating that across a reasonably small radius of GPUs. That typically is about tens of GPUs. Today, most installations are actually using only 8 such GPUs within a system. What's notable about this GPU fabric? It's 9x the bandwidth of PCIe. 9x the bandwidth. So why is it done that way? It's because it's essential to the operation of the GPU. It's 3x the lane speed of PCIe, but it's also got more input and output pins. So if it's only 3x the lane speed, that means there are actually more NVLink connections between GPUs than it typically provides to PCIe. Now, that's a design choice of the GPU maker, but it is required for these kind of very tight controls on collective GPU communication in this dimension. So now let's take that and just basically double it up. An exemplary GPU system with 8 such devices, 8 GPUs, looks like this. You can basically look at the previous slide and there are just 2 copies of it. Connected again to the network fabric and connected at the bottom with the GPU native fabric. This is actually the hardware system architecture that is predominantly deployed to support all of the AI training and in many cases, much of the inference that is currently deployed today. Many of you have heard of the NVIDIA DGX system. This is effectively the architecture of a DGX system and many other variants of that. What's interesting about this diagram is you can actually break it down into separate components. There's a CPU server, which looks like a 2-socket CPU system. There's a GPU server, which is the 8 GPUs plus its GPU native fabric, stretching from typically 8 to 64 GPUs. So it can stretch across beyond the system. And then there are this collection of PCI switches and RDMA NICs, which effectively is like a switching tray. So we can now break down an exemplary 8 GPU system into not just a bunch of components, but 3 purpose-built pieces: CPU server, GPU server, and a switching tray. When we look at that and we think of how does communication happens in this GPU native fabric over a memory semantic, okay? And we call this the scale-up dimension. For those of you, show of hands, who attended the Meta presentation this morning? Okay, so in the Meta presentation, they were talking about scale-up and scale-out. The scale-up domain is effectively this GPU native fabric that spans, a small number of GPUs, very high bandwidth. In the direction facing the GPUs towards the network fabric, this is required for scaling collectives over network. Why do we need that? Because many workloads like LLM training requires hundreds, thousands, tens of thousands of GPUs, well beyond the scope of what a GPU native fabric does today. And so there's a requirement to scale up and to scale out. And those are 2 different, complementary, not conflicting, communication requirements out of a GPU system. So let's take that system and apply it to LLM training. When we think of LLM models, the models are sliced in the GPU native fabric or scale-up dimension. Because of those tight latency requirements, tensor parallelism or mixture of experts primarily scale in that scale-up dimension. The data parallel dimension, where we're using lots of different input training sets, is what scales primarily in the network or scale-out dimension. It's also used for other types of sharded collectives like optimizer state sharding, as well as for ingestion of data, ingestion of the actual training data into the nodes. They have to come from somewhere, right? So they're coming usually from a network. When applying that system to inference, the same type of model slicing exists because it's the same copy of the model that was just trained that's deployed in these systems. And so that spans the GPU native fabric. And that is where, if you refer to the meta talk this morning, they did a great job of describing how that phase is composed of a very heavy computational phase up front that is massively parallel to compute all the prefill tokens, and then a sequential process after that to iteratively decode the next token. So this is, you get a large amount of information, like send ChatGPT a book or a volume of encyclopedias, and then that's your prefill data, and then the next token is what are the outputs that get generated from each letter that is basically predicted from the sequence of tokens coming in. So that's primarily, that computational thing is again, needs tight latencies on the decode of the next token. Not necessarily on the prefill part of that, but we'll talk about that more later. The input context, the things that actually come into the workload in order to actually seed the entire job, those are typically placed in DDR memory because they're basically the input context, the history, the prompts that we want the LLM to understand at the beginning of its work. And then there typically exists this RDMA network scaling, primarily for large inference clusters. And this is a byproduct of the fact that they are, not built on islands, and so that RDMA scaling dimension gives the ability for multiple systems to be able to talk to each other. Although today in inference, you could argue that it may not have as much density of communication on it as certainly it does not compared to training. So what are the challenges, having described how these systems map to LLMs? Well, there are three major ones from Enfabrica's point of view. One is network bandwidth for scale-out, okay? We're not talking about improving the bandwidth of the NVLink dimension, because that's the GPU's native fabric. We're talking about the network scaling in the north-south direction. That network bandwidth is critical to achieving scale and effectively to getting training times, okay? The second challenge, LLMs are latency sensitive, right? You enter a prompt, you want a response fast. The latencies that are involved at training and inference service scale, when we think about where LLMs will be a year from now, 3 years from now, get increasingly challenging because of the computational density of the problem. And then the last problem, which I think the previous panel talked about and is universally understood, is simply the cost. How much does it cost to operate a service at scale with a fleet of GPUs that are used for training and inference of these LLMs? And how utilized are those resources? Those fundamentally factor into the TCO equation of whether business models can actually work using what's being sort of set up as the parameters today of an LLM business model. So Enfabrica would like to share its perspective on this, which is consider a new approach compared to the systems that are built today. Consider that exemplary 8 GPU system as it exists now. We talked about having the switch tray being one of those components of that. Instead of having 8 RDMA NICs and 4 PCIe switches attached in kind of this stovepipe design, consider an accelerated compute fabric device, compute fabric switch, which connects all of the GPUs in this system together and also connects through multiple high bandwidth ports towards the network fabric. If the GPU fabric makes 8 GPUs look and act like one GPU fabric, should we not have a network device that looks and acts like at least 8 NICs? Why do it this way? The reason to do it is because it is a collective 8x network interface device that is impedance matched to the communication load of the collective GPUs in the system. In addition to having 8x the bandwidth, it can load distribute across those GPUs because all the connections to those GPUs are shared by this one element. Second reason, it cuts down latency of the job. By collapsing layers of the NIC, the PCIe switch, and potentially the first layer switching into the network, there are 50 to 66% fewer latency hops going end-to-end between GPUs. Because the ACFS is connected directly to the GPUs, we have better, and on the other side, connected directly to the network. It has full visibility to the traffic patterns going straight from network to GPU. We can do better traffic engineering than having disparate devices in that path. And then fundamentally, because it's a shared work-conserving element, it can mitigate the incast problem. More on that later. The last point, it significantly lowers the TCO of AI clusters. A work-conserving element like the ACFS allows GPU clusters to run hotter, that means at higher utilization. And as we'll see, it allows the opportunity to disaggregate and elasticize memory in order to scale data store without having to scale the GPU compute cost. If we compare a conventional NIC to an ACFS, on network bandwidth and on network radix, it's a significant 8x improvement. The ACFS can natively support 800 gig flows directly from the GPU to the network, and it incorporates embedded PCIe and CXL switching. But that's the speeds and feeds story. Fundamentally, network performance is very much an operationalized problem. And in that operational problem, much of that is governed by the transport layer of the network and how resilient and how performant that transport layer is across hundreds, thousands, tens of thousands of nodes. We have in the ACFS a capability to do software-defined, user-controlled transport, which means we can support RoCE, TCP, and by virtue of being programmable, support new protocols like the Ultra Ethernet Consortium out of the gate. But the transport APIs from the software point of view do not change. They align to the exact same way that transport protocols are interfaced today over infinite band verbs. Congestion avoidance is another critical factor that determines job completion time. We are capable of, in terms of the ACFS, doing better by having the ability to do multiple methods of congestion control in software paired with fast flow control in hardware, as well as the ability to do packet spraying. And then incast control is basically significantly larger pool of buffer memory in the ACFS and fully shared across ports compared to the small buffers that we typically find in individual NICs. There's another advantage of an ACFS type aggregated approach, which is that because we connect to a lot of PCIe and CXL ports, instead of connecting just to GPUs, we can connect to all memories. This is an industry first. The ability to do in-network memory allows for many AI nodes to be able to connect to an accelerated compute fabric and have access to a very large, many tens of terabytes pooled CXL memory array. That memory effectively enables a multi-GPU cluster to have an array of memory servers without the server. The bandwidth for this is at 400 gigabytes per second. Those of you might say that's nowhere close to HBM bandwidth. It's not for the purpose that HBM is being used. It's for uses where memory bandwidth is slightly lower, but the capacity that's required is much, much higher. And this latency for reading from this layer is a bounded 4 microseconds or less. Compare that with network, which is in the tens of microseconds, or flash storage, which is in the almost 100 microseconds. This allows bounded low latency, which is, again, what we require for LLMs, at least some part of that. So the idea here is network pooled memory capacity tiers that are accessible across all AI nodes can provide some significant application advantages. And this feeds, but does not actually replace. It complements HBM memory in the GPUs. So now let's talk about how. I'll give you 3 examples of how the attributes of the ACFS deliver better scaling properties for LLM AI clusters. Just as a reminder, what were the 3 items? Network bandwidth, latencies at scale, and TCO. In the case of network bandwidth and scale are basically 2 sides of the same coin. It is a function of how much bandwidth is delivered to the scale-out dimension by the GPU. Instead of using an H100, which only supplies by 16 PCIe interfaces to a NIC, we can leverage a GH200 superchip, which provides by 64 PCIe attach. And in this depicted node, we can actually deliver 12.8 terabits of Ethernet scale-out per 4 GPUs. That's 4x the bandwidth of the best performing scale-out system today on the market. Whether it's Ethernet or InfiniBand, doesn't matter. Bandwidth is 4x of what it would be in both cases. It also has 8x higher port density, which means the paths can be made diverse and spread across the switching layer above it in the network fabric, which allows a larger number of endpoint GPUs to be integrated into the cluster. So when LLM training increases inside, the ACFS is in a better position to be able to enable that scaling versus the current architectures with NICs. All of this switching is non-blocking, load balance work conserving, which allows a multi-rail of devices, and it's able to land data in any memory that's attached to this, including CPU DDR and GPU HBM, with, as we said before, user-defined transport to be able to operate and tune latencies at scale. The next point about mitigating latency. Latency basically has a significant impact in training because it affects job completion time. Critical example we can see here is where we have a burst of traffic going to a port that affects the RDMA NIC. The red means congested, and that GPU is busy and can't post a buffer. In response, it basically says a signal saying, throttle the sender. So now we have a back pressure to the sending NIC, which can cost tens of microseconds in latency because the NIC couldn't land the data in the GPU. In the ACFS case, because we have many ports going to the same device, those can all be handled in parallel by the device, which is basically grouping those ports together as a lag or an ECMP group. And those can be distributed across multiple GPU ranks inside the system, whereby the GPU, even if it's a little busy, does not have to always post the buffer where to land the data. It can come from any GPU in the system. And later, we can use the 9x bandwidth of the GPU native fabric to be able to migrate that data over. It doesn't back up the network, and it utilizes all paths in the system to be able to route to the GPU. So the ACFS has direct visibility into incast and leverages the bandwidth to be able to relieve hotspots that affect latency. We can also mitigate the latency in inference by basically having pooled CXL memory and using this to be able to pre-fill KV caches. So as LLM services grow and use much more input history and context to be able to drive into the GPUs, this tier of memory can be a capacity tier that stores all of that and grows in size without scaling the number of GPUs. It saves the recomputation of this in the GPUs and reduces the GPU computational load. It dynamically distributes this to the GPUs and reduces the queuing latency of requests. And this flat tier performs better than storing that data in CPU DDR because the memory is flat and is pooled across multiple nodes. The last point is on the TCO perspective. Reducing the problem by having this memory tier that's enabled through an ACFS allows fewer GPUs and CPUs to be required to support the same performance point of LLM inference. And this is something we've proven out in simulation and emulation, where scaling memory headlessly reduces the total XPU spend for CPU or GPU spend for LLM inference by about half. Significant when we think about how LLMs are going to grow. More things, more background data that's going to be pre-filled into services to be able to understand what to predict next. This is the part that's going to scale. not our language, but basically all of the background data. That's where we need to scale based on memory without scaling the expensive GPU compute. I'm happy to announce today that in addition to our ACFS product architecture and its solutions, that we will have the industry's first 8 terabit per second disaggregated systems that can act as GPU networking nodes, as in-network memory nodes, can connect any combination of CPUs, GPUs, and CXL memory to the network, with programmable network transport, replacing a number of disparate devices in that stack today. And this is the first to enable 800 gigabit per second directly to the server in a composable system form factor that is production grade. With that, I encourage you to engage us to learn more about our products. We're happy to talk about how applications can map to the ACFS and the roadmap of products that we have behind it. And I thank you for your attention.